Okay. Hello. Yeah. So welcome to the first session of the Bangalore Theory Seminar in this new year. Today we have our speaker, Professor Bhaskar Chaudhury, who is currently an assistant professor of operations research in the Department of Industrial and Systems Enterprise Engineering at IISc, with a simultaneous affiliation in the Department of Computer Science. Prior to this, he was a future faculty fellow postdoctoral scholar at the Department of Computer Science at IISc. And before this, he obtained his PhD from the Max Planck Institute for Informatics. His research interests lie at the intersection of economics and computation, social choice theory, and machine learning. And today he is going to talk about equilibrium theory in data markets. Over to you.
Thank you for the kind introduction. So I'm just making sure that I'm audible, right? Okay. Yeah, so this talk is most of this is ongoing work with my collaborators. So I would very much welcome any discussion, so as many questions you have, please feel free to ask in the middle of the talk. Okay. Yeah, so as the title suggests, so this is going to be on, theory of equilibrium in data markets. So I have, like Dev Jyoti said, so I have worked on equilibrium computation for quite a bit part of my research career. So mostly on market equilibrium theory. So how the project started was like we wanted to explore this equilibrium theory in a more and more increasingly relevant economy, that is the data economy. Okay, so the main takeaway from the talk, like a priori, I can say, is kind of the similarities and departures from the classical market equilibrium theory. Okay, so what makes this economy unique? What are the unique properties? How are they different? And why are they different? This is kind of like the main takeaway of the talk. All right. So this is joint work with my collaborators, Jugal Garg, who is also an assistant professor at UFI. Aniket was a PhD student at UFI when we did most of the work. Currently, he's a postdoc at Northwestern, and also with Eklavya and Jackson, who are currently PhD students at UFI. Okay. All right. So as I said, currently data, like in the digital world, with the explosion of machine learning and AI technologies, data is probably one of the most valuable assets in the digital world. In fact, Acumen Research estimates the total big data market in the United States to be around $473.6 billion by 2030. I don't know how they came up with the number, but but nevertheless, would like to say that it's becoming an increasingly important asset, and it is a very important time to study the economic processes that involve data as an asset. Okay. All right. So roughly for most of the talk, this is when I say a data market, it's not like a central entity that kind of facilitates data, like data selling and purchasing. It's more from an economic perspective where you have some sellers who hoard on large amount of data relevant, like generated from economic activities, like say Amazon, social media, or other Internet of Things companies. And then you have data buyers. So think of them as machine learning or AI companies that would like data to improve their own predictive accuracies. And what we would be interested in when I say equilibrium theory is pricing data, okay? Pricing this asset. So the buyers and the sellers, like in classical markets, they interact through the prices, all right? The stable prices are determined based on the type of competition between the sellers, which we will get to in a minute, all right? So there are different forms of competition that leads to different kinds of equilibrium prices. And we want to study the existence, geometry, computational aspects of these equilibrium prices. Okay. So once you fix the price, the buyers it would set up a unique interaction between the buyers and sellers. And now, like, there are some prices which are deemed to be stable in certain competitive environments. Okay, so the first part of the talk, like the first maybe 20 minutes of the talk, would be kind of revisiting the standard like equilibrium price theory, which I think like how many of you are familiar with competitive equilibrium? Just so that I know. Okay, so not quite a few. So it's good that we kind of go through these 20 slides. So this would tell you what is already done in classical markets. and then we would go to like data. So there will be two parts. One is what is the value for data. So this itself is a very interesting topic. I would just give you one perspective on it. This is not the unique perspective. And once we fix that, then we go into the economy, okay, and see how the economy is different. All right, so let's revisit some basic market fundamentals. So there are three forms of competition that I would be considering in this talk. The first one is, I think all of us would be aware of it. So it's monopolistic. So you have one central entity that controls the prices of all the assets in the market. Okay. So obviously, this single seller or the single agent has all the power in the market. So they are a price setter. And obviously, in these settings, the seller is going to set the price so that they can extract maximum revenue from the buyers. The other form of competition is oligopoly. All right. So in oligopolies, you have a few sellers, not a lot, but a few sellers who does have power over the prices, right? But they are not price setters because there's a competition. Okay, so there are a few sellers who are competing with each other strategically. So the sellers would be strategizing on the prices. So basically, the equilibrium price would be set to the Nash equilibrium of this pricing game. So they might undercut or overcut each other depending on how much more revenue they can get. And a price is stable when it is the Nash equilibrium of this pricing game. And then we have the most idealistic setting, which is perfect competition, where you have a large amount of sellers. Okay, so no seller has power essentially over the market prices. So sellers become essentially price takers, and the market prices are set such that the total aggregate demand of every asset meets the aggregate supply. Okay, so think of the market acting as an auctioneer. So when the market declares the prices, the buyers can say their demands, and the sellers can state their supplies. The price should be set in such a way that the demand from the buyers matches the supply from the sellers. Okay, so these are just giving you a very informal overview of what are the stable prices in different forms of competition. Okay, we'll make all of this formal in a second. All right, so let's go through the solution concepts in each of these rivalrous markets. So this is what I call rivalrous markets, okay? Classical markets or rivalrous markets. So the rivalry is, just giving you a heads up. So this is kind of where the data markets would be like very different. All right, so when I say an asset is rival, it means that the availability of this asset for one buyer is affected by the consumption of this asset by the other. So for instance, if there are 2 apples in the market and there are 10 buyers, you cannot have all 10 of them leaving with an apple, because like if one buyer takes an apple, it's not available for the other buyer. This is different for data, okay? Or for digital goods, generally speaking. So these are freely duplicable assets. So this is kind of what's going to introduce a fundamental difference in the economy. So I'm just giving you a heads up, just have this in mind. Nevertheless, we'll kind of revisit the solution concepts in the rivalrous markets quickly. So the market that I would be considering is a specific form of perfect competition, which has been studied in the econ-CS community quite actively since the 2000s. This is called the rivalrous Fisher market. Okay, in a Fisher market, you have n buyers. So this is a formal model. You have n buyers who are budget constrained. So the budget of agent AI is BI dollars. This is the maximum amount of money that they are willing to spend in the market. And then there are n divisible goods. All right. So these goods can be fractionally allocated. So think of that you have large, like they need not be divisible as per se. You can have large quantity of these goods that you can make sense of. Like fractional allocation makes a decent, like it's a reasonable abstraction of the market. So you have m divisible goods. All right, and the preferences of the buyers over the goods, I would. For most of the purpose of this talk, I would stick to what we call linear separable preferences. So what this means is that you have a utility matrix over here, which captures the preference of the buyers. So Uij is the utility that buyer I has for 1 unit of good J. All right. And the utility that a buyer can get from a bundle is the sum of utilities they get from individual goods. And the utility that they get from each good is Uij times the amount of this good that is being consumed. So they are linear and separable. So these are the utilities that I would be considering for this talk. All right, so now we are looking at a solution concept, which is called competitive equilibrium. Okay, so this is a fundamental solution concept in Fisher markets. So recall that in perfect competition, we want to set the prices such that the demand equals supply. So in Fisher markets, we assume a fixed supply. You can also look at a variant of the market where the supply is variable, but we are not going there for the purpose of this talk. So there's a fixed supply, which is the amount of these goods that are being produced. And now I want to set the prices such that the demand from the buyers equals supply for every good. So what does that mean? So let's say that I arbitrarily fix prices of these goods. Once you fix the prices, each buyer is going to demand a bundle which is going to maximize her utility subject to her budget constraint. Okay, so the buyer is going to demand the buyer is going to demand the most valuable, affordable bundle. So in particular, let's say that we have this vector xi to denote a buyer's bundle, where xij is the amount of good j that buyer I is demanding. All right, so xi, this vector, should be utility maximizing bundle for I at P. So what it means is that xi should be the solution to this optimization problem, which is maximizing summation over j uij xij, subject to that the total cost of the bundle, which is pj times xij, is at most the budget that the buyer has. If you look at this carefully, I mean, this is like a fractional knapsack, right? So for every item that you consume, there is a utility and there is a cost. So you can already characterize the optimum bundles of the buyers. So every buyer is going to only consume those goods which have maximum utility to price ratio or maximum bang for buck ratio. Okay. All right. And now, when is a price a competitive equilibrium? So price and an allocation is a competitive equilibrium if the allocation is the optimum demand bundle for every buyer at this price, and the total demand for a particular good, which is sum up over the demands from all the buyers, the total aggregate demand should be equal to the supply of the good. This should be satisfied for all the goods at the same time. Then a price vector is a competitive equilibrium. It's a market clearing price. Any questions regarding, I mean, okay, so maybe let me show an example and then things will be clear. You have a question?
Is it possible that for some buyer that bundle has goods that contain different levels of bang per buck? Because
Not
some good has lesser supply.
No, so buyers are not supply aware.
Okay.
So that's the whole point, right? So the auction is so typically the buyers are not supply aware. So that's the whole point of the prices. So if buyers don't know the supply, and when you declare the prices, the buyer is saying that, okay, I'm gonna, like, I don't know how much supply there is, but I want this much of this good for my utility. There's a point of the market to choose a price such that it matches the supply. If it doesn't, that means you're either over demanding it or under demanding. But yeah, good point. Yeah. So yeah, short answer is no. Like the optimum bundle will always contain bang per buck goods. So here's an example, like just so that we get a sense of competitive equilibrium. So you have three agents here. These are the budgets of the agents. The first one has $1, the second and the third has $0.25. There are two goods, G1 and G2, and this is the utility matrix. As you can see, all the three buyers prefer the first good over the second good, strictly. Okay, but by different amounts. The first one prefers the first good 3 times than G2. A2 and A3 prefer it 1.5 times for G2. Okay. All right. So here is a price where I price them equally, 3, 4, 3, 4. I choose the prices such that they equal to the sum of budgets because that would be required for the market to clear. But the main point is both the goods are identically priced. Now you can imagine that this is not going to be a competitive equilibrium because if both these goods are identically priced, and all the agents strictly prefer the first good over the second good, they're all going to demand the first good and nobody's going to demand the second good, right? So I'm not going to go into the details of these numbers, but they're believable that if you look at the optimum demand bundles for each of the buyers, they're only positive in the first coordinate because they only want the first good. Okay. So if you look at the total aggregate demands at these prices, the first good is over demanded and the second good is under demanded. Okay. So the market itself tells you how to adjust the prices. So obviously, since this is over demanded, you need to increase the price. And since this is under demanded, you need to decrease the price. In fact, most algorithmic solutions to finding this equilibrium kind of work this way. Okay. Anyway, so let's say that I do this, but I do it a bit too much. So earlier they were 3/4, 3/4. Now I make them 5/4, 1/4. So now the price of the first good is 5 times the price of the second good. Okay. At these prices, you can see that the opposite is going to happen. Yeah, all the agents do strictly prefer the first good over the second good, but not 5 times more. The max is 3 times. Right? So now if you look at, if they go by their bang per buck, everyone is going to demand the second good and no one is going to demand the first good. So you get the first coordinate of all optimum demand bundles to be 0. And the first good ends up being under demanded and the second good ends up being over demanded. Okay, so the opposite is happening. So at some point in the middle, like I should have achieved an equilibrium, and that is exactly what happens. So if you set the price to 1.5, you can verify that the first agent now, again, he's going to only prefer the first good because it's 2 times price, but he likes it 3 times more. All right, so he's going to spend the entire $1 of money on the first good. So this is his optimum demand. But for the second and third agents, this is a better good. It has a better bang per buck ratio. So they're going to spend their entire budgets into the second good by demanding half of the second good each. And that way you have demand equals supply for both the goods. All right. So this price 1.5 is a competitive equilibrium in this instance. All right, so what is known about a competitive equilibrium? So first, one of the seminal results in microeconomics is a competitive equilibrium always exists. No matter how many agents you have, how many goods, and whatever the utility matrix looks like. In fact, the first result holds even more generally. Even when agents have, say, quasi-concave utility functions, the first result holds, okay? Then a lot of studies have been done on the geometry and algorithms computation of this equilibria from the CS as well as the econ and the OR community. This is just a very small sample of results. There are many more papers which I have not put here. But one thing I would like to point is that this equilibrium has a lot of nice properties, at least when we consider, say, separable linear preferences, that in particular there exists that you can express the equilibrium as, say, KKT points of a convex program. And this convex program, in some sense, aids all these algorithmic results too, like the natural atonement dynamics, as well as the combinatorial algorithm by Devanur, Papadimitriou, Sabiri, and Vazirani, and also the strongly polynomial time algorithm by Olin. Okay, so competitive equilibrium exists. All right, it has a nice property that the equilibrium prices. Actually, in fact, you can prove that equilibrium price is unique, right? Not just that, like the equilibrium, it forms a convex set, but you can prove that the equilibrium price is unique. So many nice properties, all nice computation results. So everything is very good. Okay, so now let's move to the other form of competition, which is oligopoly. Okay, so recall oligopoly, where you have few sellers, and now they are not price takers. They have some power over the market clearing prices. And the equilibrium price is set to the Nash equilibrium of the pricing game. So what it means formally is that every seller gets to choose the price of their asset. Once this price is chosen, the seller's utility is essentially his revenue, which is Pj times the total demand for this good. Okay, so once the seller sets all sellers set the price, the buyers are going to best respond. And this is the total revenue that seller J collects. Okay. So given the other seller strategies are fixed. So a P is stable if it is a pure Nash equilibrium of this pricing game. Okay. Now, a very interesting result is that when agents have linear separable preferences, competitive equilibrium is also the Nash equilibrium of this pricing game. Okay, so the solution concept that holds for perfectly competitive environments also holds for oligopoly. Why is this? I'll give you a quick proof sketch. It's not that hard. Think of it this way: that say you have the prices are set such that demand equals supply. Okay. Now look at the first seller. Is there any incentive for the seller to decrease the price? No, because the entire supply is being sold. So even if you decrease the price, your revenue is not going to go up because you're selling the entire supply. Right? So you cannot sell more than what you're selling at this price. So it doesn't make sense to decrease the price. Now, does it make sense to increase the price? No, because for agents who are spending their entire budget, you're not going to get more money. And for agents who are spending some part of their budget, they're not going to spend on you anymore because the bang per buck can change when you increase the price. So it can only reduce the revenue that you collect. Yeah. So this would be, I mean, I just hand waved slightly here, but still, I mean, I'm sorry about that. Yeah. So, but yeah. So it is well known that the prices at competitive equilibrium is also a Nash equilibrium of this pricing game.
But this is not true for the data set.
Yeah. So yeah, very nice. So this won't be true because this thing that I said right here, right? This need not be true in the sense that
There's no supply.
there is no kind of supply when it comes to it. Like we have to revisit the competitive equilibrium definition itself, and even with meaningful definitions, you will see that this will break already. Okay, so finally, there is this monopoly. There's a single central entity that gets to choose the price for each asset, all right, or each good. Once you fix the prices, the buyers will best respond, give their optimum demand bundles. So you want to set the price such that you maximize the total collected revenue. It's also called the Stackelberg equilibrium because the central entity is the leader and all the buyers are the followers. Once the central entity sets the price, the buyers best respond with their optimum demand bundles, and you want to set it such that you maximize the total amount of revenue. Now, one observation is that this problem is trivial if buyers have no value for money. Input, that means that if UI of xi, which is the utility the buyers get from their bundle, is independent of the amount they spend, which is the assumption we are making, right? The UI of xi is summation uij xij. So in some sense, this setting doesn't make quite this setting is not very meaningful in monopoly because the buyers are coming with a mindset that I'm going to spend my entire budget. Okay, this only makes sense when buyers have value for money, right? And even in that case, some of the results I said earlier will still hold, right? I mean, just for simplicity, I didn't include them. So in particular, there is what we call quasi-linear utilities. So our quasi-linear utilities, the buyers have value for money. So the only difference is that the utility of the buyer is not uij times xij, it's uij minus pj times xij. Okay? So for instance, if you arbitrarily price it very high, the buyer might not demand anything. Okay? All right, so now let's say that the buyers have quasi-linear utilities. The seller, the single seller, the monopolist sets the prices of all the goods. The buyers must respond with their optimum demand bundles, and the goal is to maximize the total earned revenue. It turns out that a competitive equilibrium with quasi-linear utilities is also revenue optimal. Okay, so it's a recent result by Finster, Goldberg, and Locke. It's not that hard. The arguments is somewhat similar to the oligopoly argument that I showed. So you can actually work it out. It's not very difficult. Okay, so the main takeaway is
Quite likely I should know this, but have there been works that look at the oligopoly pricing game with quasi-linear?
Yeah. So yes, I mean there are. I mean, I haven't seen any paper that does that, but you could do that also. And I believe that the same argument will go through what I said earlier. Because the main difference what comes to when you have quasi-linear is that the buyers will still demand bang per buck, but the bang per buck needs to be larger than 1. Like if the PJ is larger than the UIG, the buyers are not gonna demand. And I think that will still go through. Okay. Okay, so now we move to, so the main takeaway is that for like very structured preferences, like the ones we consider, there's a single solution concept which works in all of these settings. Okay. So now let's move to data markets. So in particular, as I said, I would first start by understanding the value of data. So you can ask me a lot of questions. This is just, say, one way of modeling it. And then we'll talk about data, like the economics that arise. Okay. So first of all, I think the main challenge is, like, what do I mean? Like, all the utility functions that I defined are like for homogeneous goods. What I mean by that is the utility you derive from a good depends on the amount of that good consumed. What does that mean in the sense, like when it comes to data? Because if you think of data as information, like it should depend not just on the amount of, like, what does it mean, amount of information also? So let's add some meaning to that first. So for the value of data, we're going to pursue Shannon's information theoretic perspective that data is anything that reduces uncertainty. Okay. So what that means, so data is so we have agents, like in particular, we have consider an agent who wants to estimate some unknown state of interest, let's say theta, and the agent has some prior belief. So this prior belief could be nothing. All right, I know nothing about this thing. So very high variance for this thing. And data is a signal about this state. So once, like it's a signal S. So if I get the signal S, which is correlated with theta, then I get some more information about theta. So once the agent gets the signal, the agent updates the belief to the posterior. So theta given S. And the value of this signal is defined as a reduction in uncertainty. In this case, I choose reduction in variance as you move from theta to theta given S. Okay. So let's make this a tad bit more precise. So for the purpose of this talk, I'm going to assume that a data set of a seller is a collection of data records. Now, the data records is free to interpretation. So data records are the tokens in which the seller is willing to release his data set, right? So each data record of a seller is a noisy signal to the buyer about his underlying state of interest, okay? So once he gets the signal, the buyer does some post-processing, and then he gets some information about theta accompanied with some noise. Now, this noise depends on the relevance of this data set to the buyer. So if this data set is very informative, the noise is going to be 0. Okay? So if it is not, then we'll have some amount of noise. And the value of the data record is defined as the prior variance minus the expected posterior variance. So you take the expectation over S. Okay? So this is what I say the utility of this data record is for the buyer.
It's assuming that the buyer knows this.
Yes, I mean, so here I'm actually defining the utility. So your question is, is the buyer aware of his utility? Yeah, so that's a great question. So I mean, for this talk, I would be assuming yes. So the buyer knows about the credibility of the seller in some sense and has an idea about these distributions, which I'll get to in a second. But that's also a very interesting line of interest. So the seller strategy could be more nuanced in the sense that the seller can give some data records for free. The buyer can observe the reduction in variance and can estimate what would be the reduction for the rest of the data set. So you can have more nuanced strategies also. Yeah. Okay, so one more thing I would like to say is that you can also interpret this as the variance of the expectation of theta given S by the law of total variance. So what this means, like if this looks confusing, don't worry about it, but still. So what this means is that if your signal is very informative, it should lead to substantial different realizations of theta. Okay, so that's why like the expected value of theta once you observe the signal should have high variance if your signal is pretty informative. So this almost follows from the law of total variance, but nevertheless, that's another way of looking at the value of information, but the more natural way is to look at, say, the reduction in variance.
Yeah, like, maybe a digression, but is entropy also good?
Sure. Yes. So this is just one measure. You can use many. So this measure is chosen because with this we will be able to replicate the utility forms that we see in classical markets and draw parallels and distinctions. But yes, you can consider anything which makes sense, which can quantify uncertainty. Yes. I couldn't
The motivation for predictive model. This is
Yeah, this is pretty much like following standard in controls, but yeah, I mean that's one more direction for future. So in particular, like instead of like okay, so this is for one signal, right? So when you have say multiple signals, like if you have additive, you get additivity in the reduction in variance, some sort of an additivity in the reduction in variance, which helps you kind of draw parallels to the classical. But yes, you can consider more informative signal structures. And there are few, like for instance, two signals can be complementary, right? So one data set for healthcare, like one could be a blood report, one could be a scan. Individually, they are not very informative, but when you put them together, they can kind of reveal more about an underlying state. You can study those, and those also lead to some nice utilities which are studied in economics. We call them beyond TF, but we don't do that here. But that's also a very nice direction for our future. Yeah. Yes.
The choice of quantifying this
Yes.
is going to affect the looking ahead.
Yes, it is going to affect because, as I said, so the equilibrium generally, game theory is very sensitive to the utilities. Whenever you're talking about stability, because we are talking about agents best responding, right? So, like we are talking about optimal solutions to some so we are talking about optimal solutions to some optimization. So if this optimization is not well behaved, these optimal solutions can jump. Like so when they jump, then usually equilibrium guarantees we can't give. Like for instance, if the utility functions are not concave, then essentially all of game theory gets wrecked. So that's like yeah. So this form would give us a nice form of utilities with which we can say something about an equilibrium. That's why, yeah, you're right. So I mean, I'm choosing exactly this form because I'm talking about utility. But I feel that generally speaking, this is how, like, this is a more general way to look at, say, the value of data. And like Siddharth said, you can use other measures too. You can use entropy. You can use many other measures that you feel like. Okay, so let's investigate this in our setting. So recall that we have n buyers, budget constrained buyers, and each buyer has an unknown state theta I to predict. Okay, and there are m sellers. Each seller owns a data set, and each data set is a collection of data records. So SJ data records, let's say. So each data record of a seller is a noisy signal about theta I to buyer I. Of this form. So Sij is theta I plus eta ij. So eta ij is the noise, and this noise depends on how relevant this data set is for buyer I's prediction task. Okay? So once the buyer, so again, you can define the data bundle like before. So Xij is the number of data records from seller J that buyer I that buyer I demands. So more the number of data records, like most of the time you can believe that more the number of samples you draw, higher should be your predictive accuracy. Okay, so that's how you can interpret this data as a homogeneous good. So each data record is like a sample drawn from DJ. Okay, which gives us which gives information to the buyer about his underlying unknown state. Okay, so the utility for a data bundle Xi, so if let's say S of Xi is the set of all observed signals, is a reduction in variance that you get as we did before. So once you observe all the signals. And under, say, for the purpose of this talk, I'm going to make more assumptions. Like I'm going to make an assumption that this underlying state of interest follows a Gaussian, like centered at the mean, and this is the prior variance. Okay. And each of these eta ij's follows a distribution with zero noise, and this is the variance. So this kind of depends on how relevant the seller's data set is to the buyer. So this quantity, the buyer knows a priori or has an estimate a priori. Okay, so is what I was saying. So this implies that the noises across the sellers are independent, and the signal and the underlying state, like signal is correlated, the signal minus the underlying state, which is the noise, is independent of theta. Okay, so these are also two assumptions, which are like somewhat standard in controls. And under these assumptions, you can get this nice closed form expression for the utility function. Okay, so this is the prior variance that you have. And this is the, like, since it's Gaussians, you can actually show that expected variance is not, like the variance is not, the expected variance is non-stochastic. And this is exactly what you get. So tau I plus summation over j, tau ij times xij. So more the number of data samples you consume, the more is the reduction in variance, in posterior variance. Okay. Okay, so if you look at this utility function, all right, and if you look at the like objective of the buyer, which is to maximize this utility function subject to some constraint, these are basically budget constraints. If you want to maximize this, it's essentially the same as maximizing this quantity over here, right? Because, and this way we can at least talk about, say, data markets where agents have linear preferences, separable linear preferences. But yeah, I mean, as you pointed out, that you can have, say, a richer signaling scheme, and you can have this instead of over j, you can have it over sets S, and replace this xij with minimum or I in S. So that's the form that you would arrive at. Like if you're looking at, say, richer signaling schemes, and that's also studied under, say, Leontief utilities, but we don't study that. I mean, that's a natural direction for the future that we can look at. Okay. Alternatively, you can also define it to be the improvement in precision that you get. So precision is defined as the inverse of the variance, in which case you will also arrive with this formulation for the utility, the linear separable form of the utility. Okay, so once we have the value of data fixed, so let's talk about the data markets. All right. So as I said earlier,
like till this point, like again, I know the supply aspect will
right,
make things complicated, but if I like look at the utility model, it actually is like the classic setting.
it is like the classic set. Yes, I mean, I'm just giving something like mathematically, it is like the classic setting. It's just that I was giving some more of a justification to where the value of data comes and what it is meant by looking at it as a homogeneous product. Yeah. Okay, so now comes the difference, like main difference in the nature of the asset. So this is data is a non-rival asset in the sense that it can be duplicated at zero marginal cost. So as a result, like if you have, say, one apple, you cannot have two buyers leaving with two apples because it's a hard supply constraint. But if you have one data set, you can have all sellers leaving with a copy of the data set, or like whatever, like or using the data set at the same time, whichever is the model of the market. Okay. So in some sense, like once a data record is available, its supply is infinite in some sense. It's available for all buyers. Okay. So then let's revisit our frameworks. Let's look at perfect competition. So we defined the solution concept from perfect competition, and we said that it served as a solution concept for the other economies as well. So in perfect competition, recall that once you set the prices, the buyers are going to best respond with their optimum demand bundles, and we wanted the total aggregate demand to be equal to the supply. Now, this doesn't make any more sense because data is non-rival. So this need not be the total aggregate demand. A single data record can be used to service all the buyers. Okay? So competitive equilibrium doesn't quite make sense. But let's say that we want to follow the main underlying principle behind competitive equilibrium, which is that everything produced in the market needs to be consumed. I mean, otherwise it doesn't make sense to produce. Okay? So if we were to follow this philosophy, a natural market clearing condition is this. I mean, trying to keep things as similar as possible to the previous literature. A natural market clearing condition is you replace the summation over here with the max operator. Okay? So in particular, like if I have 10 data records which are available, but no one is demanding more than 9, then one data record is being unnecessarily produced because I can service all of them with just 9 data records. So the new market clearing condition says that there should be at least one agent that is requesting SJ many data records. I mean, otherwise otherwise your demand is below the supply. Okay, so with this new market clearing condition, so we asked the same question. So we defined competitive equilibrium. The first condition is exactly the same as before, no difference. Market clearing condition is now different. Instead of aggregating it with the summation operator, you aggregate it with the max operator. So what does this create? What difference does this create? So let's recall. So we saw that in rivalrous markets, a competitive equilibrium exists, and not just exists, the competitive equilibrium price is unique and rational because of the Heisenberg-Yale convex program. It turns out that the same guarantee holds. Okay, a competitive equilibrium exists, and the competitive price is unique and rational. It was somewhat surprising to me because, like, at a very intuitive level, this condition seems to be more relaxed than this, because here you just need one buyer to consume all the data records. You don't care about the demand from the other buyers. For every data record, you just need one buyer. But despite that, the competitive equilibrium price is unique, right? And rational. Now we know as a result of the convex program, so typically these convex programs, they're defined in just one space. Like there are two variables, right? Allocation and prices. These convex programs are either defined completely in the allocation space or in the price space. So the price acts as dual variables to the constraints in the allocation space. So because of the duality, you can say that at the equilibrium price, the set of competitive equilibrium allocation is also convex. But this is no longer true because the max operator does not preserve convexity. Okay? So you can have a unique competitive equilibrium price, but you can have multiple, like you can have like non-convex competitive equilibrium allocations. So it is quite unclear, like a convex program is known for the rivalrous case, but a convex program, it's unclear like how to come up with a convex program here. Because I don't think it's that easy to do it like only in the allocation space because of this primal dual nature of the prices and the allocations. Okay, so we don't know a convex program, and as I said, most of the computational results are guided by this convex program, which we don't have over here. But despite that, we are able to come up with a very simple combinatorial auction-style algorithm, which is an F-beta, so it computes an approximate competitive equilibrium in time, which is polynomial in the size of the instance and 1/epsilon. But I mean, we don't know to compute an exact competitive equilibrium, so that's a question which is naturally open. And since we don't have a convex program of sorts, we are not even sure of whether that's like, it's an interesting thing to consider whether there are natural market dynamics that converge to a competitive equilibrium. Because usually these market dynamics, like increase the price when it is over demanded, decrease the price when it is under demanded, are seen as first order methods on this convex program. You can interpret them, which we don't have anymore. But still we have a natural auction style algorithm which does exactly that. I mean, not increasing price by the excess demand, but at least in the same spirit, increase prices when it is over demanded and decrease prices vice versa. So perhaps there is a market dynamics, but maybe the usual analysis is not the way to go about it. So are there some natural market dynamics that converge to a competitive equilibrium in data markets? Okay, so I think I still have 15 minutes, so I'll quickly cover the other two settings. So recall the oligopolistic setting.
If this is like, how does it, the algorithm that you have is not a dynamic, like it's not.
It's not a dynamic, but it is in the same spirit. So the dynamic changes the prices by the excess demand, some scaling factor times the excess demand.
Yeah.
We will not do that. We will increase the prices in a more controlled way at depending on what the other prices look like and stuff, depending on the configuration of the bank per buck graph. So although it resembles the same spirit, like you increase prices when demand is more, decrease prices when demand is less, it has the same spirit, but it's not exactly the same thing. Yeah. Okay, so recall that like in oligopoly, like it's a Nash equilibrium of a pricing game, and recall that in the rival risk case setting, we had competitive equilibrium implying the Nash equilibrium. So here, unfortunately, with our new definition, this is not the case. Okay, a competitive equilibrium need not imply a Nash equilibrium in oligopolistic data markets. But now let's revisit a fundamental question. Like, does a Nash equilibrium always exist? And surprisingly, the answer is no. I can give you an example here. It's a small example. I mean, I will not, maybe I'll spend some time. Okay, I'll just cut some time from the monopoly section. So here is an example. I will just give you a sketch. The detailed proof is a little involved, where I can show you that there is no Nash equilibrium. So imagine you have 100 buyers with $3 of budget and 101 buyer with $10 of budget. And there are two data sets, D1 and D2. Okay, so let's start with these prices. Yeah, and all these 100 buyers, they prefer the first data set 5 times. The tau ij basically is 5 times more than the second one. And the 101th buyer, they only care about the first data set. This is absolutely irrelevant to them. So if you can verify, this will be a competitive equilibrium, this price that I wrote here, 10,2. So what happens at 10,2 is that this guy is going to spend $10 of money and request all the data records that are available, clearing this. And these people, they can spend on both of them. They have the same bang per buck ratio. So they can spend, say, $1 there and $2 here. Okay, one feasible allocation. If they spend $2 here, so all of them are querying this data set. So this is a competitive equilibrium. Well, is this stable? No, because this guy has an incentive to reduce the price. As of now, these 100 buyers, which is where the main bulk of money is coming from, they are indifferent between these two data sets. They have the same bang per buck. But now this agent has an incentive to reduce the price and pull all this money. This was not possible in the rival risk case because you're selling your entire supply. But here, in some sense, these buyers are independent in some sense. Like the availability of this data set for one buyer is not affected by the consumption by another. Okay? So yes, this guy will reduce the price and he's going to pull all these 100 buyers towards himself. All right, leaving this seller with nothing, with $0 of money. All right. So then what happens is that the second seller is going to undercut again to pull all these 100 buyers. So they always have an incentive to do this until the single data set is sold completely to all buyers. Right. That's kind of the structure that this part of the instance is enforcing, which is a very strong structure. I mean, this will create some irregularities which would require something else and then show that no Nash equilibrium exists. So what happens is that this undercutting will go on until say the prices are like 2.5 and 0.5. At 2.5 and 0.5, again, these 100 buyers are like, they have the same bang per buck. They're going to spend $0.5 of money on this, on the second seller, and they're going to spend 2.5 on the first. The second seller has no incentive to decrease the price because the entire data set is sold in its entirety to all the buyers. Okay, so no reason to decrease. And also no reason to increase because then all of them are going to push their money to the first seller. This is fine. What about the first seller? Again, no incentive to decrease, right? Because anyways, these guys are going to spend 0.5 and then give him 2.5. So there's no reason for this guy to reduce the price anymore. But there is an incentive to increase the price. Because if you increase the price, even if these agents go to this seller first, they're still going to give you 2.5. And you're getting more money out of the last seller, last buyer.
Why D1 would still get?
So this is an oligopoly. So in an oligopoly, so in a competitive market, they will only spend on bang per buck. In an oligopoly, these agents are like the agents are supplier. Otherwise, it doesn't make sense. Okay, like they will spend their entire money on this. They're going to exhaust it because there is no demand equals supply happening in oligopoly. All right, so they're going to exhaust this entirely. So even if you make it 2.6, let's say, so they will spend 0.5 here and they will spend 2.5 here. So you're not losing any money from these 100 buyers, but instead you're gaining more money from this last buyer. So you will increase it, and then the same thing will happen. So there's like a rough sketch of why, like what kind of instability you will see in data oligopolies. Okay. All right. So oligopolies are unstable. All right. Contrast to rivalrous goods. So what happens in monopoly? So monopoly is a revenue maximization, right? So recall that this is kind of the utility form that would look like the utility minus the cost of the bundle for every agent. And you want to choose a price such that you can extract the maximum amount of revenue from the buyers. Okay. So earlier, we knew that competitive equilibrium is also revenue optimal. And competitive equilibrium can be computed in polynomial time, as a result of which revenue optimality in rivalrous case was in P. But this is no longer true. You can show that revenue maximization in data markets is APX hard. So you cannot come up with, so it's highly unlikely that you come up with any algorithm. Okay. But despite this, you're able to give an online 2 approximation algorithm for maximizing revenue. Okay.
Yeah, FPTAS and this APX hardness means that such an implication might not exist.
Might not exist, exactly. So no competitive equilibrium or no reasonable definition of a competitive equilibrium which can be computed in polynomial time would give you any guarantees for revenue optimality. Yeah, that's kind of what it implies. So finding polynomial time verifiable necessary and sufficient conditions is unlikely. Yeah, so, but despite this, we come up with an online 2 approximation algorithm. And I won't have time for this, but this has a very nice, cute connection with K submodularity. But I mean, if you're interested, you can ask me after the talk. But we basically end up showing that the revenue optimal pricing, you can kind of tweak it and like you can tweak. So as of now, the pricing space is continuous. But you can focus on a discrete pricing space, which should not be too hard to see because it only makes a difference to a buyer if the UIJ is equal to the PJ in quasi-linear. Yes.
Show the definition of K.
Yeah. So K submodularity, instead of like you have a ground set and you have K disjoint tuples,
Okay.
it's monotone and this diminishing marginal returns hold under each coordinate. Yeah, that's what K submodularity is. Anyways. So I'm not getting into this, but we can prove that like you can restrict yourself to some discrete pricing space, and in that space, this revenue function becomes n submodular, and therefore we can get 2 approximation by using the 2 approximation for n K submodular optimization. But in fact, there's even more structure And one can even show that the revenue maximization in data markets can be modeled as submodular optimization subject to partition matroid and get even a stronger approximation guarantee. Okay. If you're interested, we can talk about this later. Offline, yeah. So. Oh yeah, sorry. Yeah, this thing is offline. This is offline. Yes, correct. This is not online. Okay. So now, I mean, I skipped through all of that. Despite 5 minutes to come to this slide, which in my opinion is, at least in when I was working on this was the most interesting insight for me. Okay. And this will take a separate talk in itself. So I'll just mention what the insight is. So one question that comes is that why are we restricting ourselves to pricing functions that are linear? Throughout this entire talk, we are looking at linear pricing functions, right? So look at, like, by linear, I mean like the price is some constant times the amount of this good demanded. So what happens when, say, a monopolist or oligopolist optimize over, it's slightly informal, but say a larger, more general pricing functions? So one question you can ask is that why was this not done in the classic case, right? So apart from the fact that one thing is that when you look at the optimal strategies of a monopolist or an oligopolist, you will see that the optimal pricing functions would be convex in the sense that with increasing marginals. Like so basically saying that the first 10 apples you pay me like $5, the next 10 apples you pay me $20. Which doesn't make sense in the rival setting because the buyer can just duplicate himself. Like the buyer can just come back again as a fresh buyer. But in the context of digital goods or in the context of data, these pricing functions make more sense because the data records, I mean, although like we model them as samples from a distribution, they are released in some like fixed pre-order. That's kind of what we assume. And in that case, like even if a buyer duplicates themselves, he ends up getting the same set of data records.
You can think of them as episodes.
Yeah, you can think of them as episodes. Yeah, you can. So the buyer ends up getting the same set of data records post duplication, and resulting in no information gain. Okay, so this kind of pricing makes more sense in non-rivalrous setting. But the main question is that the bottlenecks that we saw, right? An oligopolies are unstable, monopolist optimal strategy is APX hard. Does it make the problem easier or harder? It's unclear because we are having a more general space of pricing functions. Surprisingly, it turns that the results are positive. So the monopoly, like the revenue optimal strategies, the Stackelberg equilibrium ends up being, we can compute it in polynomial time. Because the structure of the pricing functions, like the optimal pricing functions have such a nice structure that you can write this optimization as an LP. It ends up we can write it as an LP and then we can compute it. And also we can give some kind of an approximate Nash equilibrium guarantees in the pricing game, which is also pretty interesting. So basically saying that if you have more general pricing functions, then the optimal pricing strategies don't change dramatically when the best response of the others change by a little bit. Like this kind of a property we are able to get when you kind of go to a broader pricing strategy. So to summarize in this talk, I introduced a framework for studying equilibrium theory in data markets. We saw that the rivalry of data calls for a new notion of competitive equilibrium. Under uniform pricing, we saw that oligopolies are unstable and a monopolist revenue optimal strategy is hard. And beyond, like if you go beyond uniform pricing, we get some cure. I think I should change this, it doesn't fix, but we get some cure to the existence and computation issues. And obviously there are many directions like of complexity, hardness, and dynamics that I mentioned, say somewhere in the middle of the talk. There are also many modeling directions. And one of them, as was pointed out, say more informative signaling structures. So it can lead to very different kind of utilities, and you can investigate all of these questions that I said. And you can also look at oligopolies, which are somewhat different. So these oligopolies that are considered, they are pricing games. There are also oligopolies which are supply games. Like the prices are announced, they come from the market, but the sellers can decide how much to supply, how much to produce at these prices. Okay, so that's called a corner oligopoly, which I did not, which we did not investigate, but it also seems like a very natural direction to consider. Yeah, that would be all.
Just a technical curiosity. If you go back to the slide where you had this max thing for the
Sure.
supply, like the definition of like yeah. Yeah.
Oh, sorry.
Yeah. Okay. So right in the bottom. So just a technical curiosity. So the difference between this and a standard Fisher market is you have a sum there instead of a max. I'm wondering how sensitive it is to this. So I could have in fact looked at like I mean this is completely technical, just an abstraction.
Sure,
Let's
sure.
say I look at an LP norm of these exercises. So
Yes.
if you plug it as L1 norm, you get your standard CE, L infinity usually.
Yes.
Yeah.
I think I did think about this for a second. So, yeah, this first result, I think you will be able to show. The computation, it's unclear to me. I don't think of it very, very deeply. But yeah, I mean, and in fact, you can get even more structural results, which I did not mention. Like, for instance, you can prove that when you're using the L infinity, like the max here,
Yeah.
that every equilibrium price
Yeah.
is going to be less
Okay.
than the equilibrium price, like when you're using L1, which means that every agent is going to get more utility because the utility is the budget times the bank per buck. So if all the prices are not as high, then it means they're going to get at least as much utility in the non-rival, which is intuitive, right? Because the resource is available for more people. But you can prove it that the utilities of all agents is greater than equals to the utilities in a rival list. I think it would be interesting to see similar properties for say something between say p equals to 1 and p equals to infinity also. So there are say more structural properties which also my guess is it holds through. Yeah.
This max condition, if you were to remove it altogether, let's say Meta has data, it doesn't want to sell all of it if it doesn't get the right price for it, whatever reason. What happens to the results? Like what happens?
Yeah, so the max condition only makes sense in perfectly competitive settings.
Okay.
Like when there are so many sellers, right? I mean, of selling similar kind of like product that it is basically that everything produced has to be consumed. Like that's like the market law.
Okay.
But yeah, I mean, the setting that you're describing, it seems like a few big players, like
Yeah.
Meta. So that will go into the oligopoly setting.
Okay.
So that, which is very different than this as we saw.
Yes. The API card has like what predictions do you?
So that's interesting. So I think it's vertex cover, to the best of my knowledge. But yeah, there was one more hand. Yeah.
Yeah, so starting off, you mentioned something.
Yeah, the convexity, non-convexity, uniqueness of the price, these things. And also like towards the end, the geometry of the optimum pricing functions, they are like if you optimize over the space of all monotone continuous pricing functions, you will find that the optimal monopoly strategy is like it's piecewise linear convex. Also, like, there are some results which I hit.
No more questions. Let's thank the speaker.
Thank you very much.
Mhm.